take on the first part, 6.1, refraction of light. Okay, this situation, I think you will observe it almost every day. So you put a spoon into the water, you can see the spoon appear bends in water. Or you put a glass block, you can see suddenly the words of the book become bigger. Okay, so why is this situation occur? What concept that we can use to explain this situation? So that's the concept that I want to discuss today. It's about refraction of light. What is the meaning of refraction of light? As we know that light always travels in a straight line. That's why our line of vision also is straight line. So what is the meaning of refraction of light? Is the bending of light due to change in the velocity of light when traveling through mediums of different optical densities. So when there is change in the density of medium, it will cause change in velocity. When there is change in velocity, it will cause direction of the light to bends. Look at this ray diagram. So this is incident ray, maybe coming from a ray box, incident towards a glass block. So you can see the light ray travel from air to glass. The line that separates the two medium, which is less dense medium, you can say air, or the denser medium, we can say example as glass. So this line is a boundary line that separates the two medium. So when incident ray is incident at this point, what we do is we draw a normal line. A normal line is 90 degrees to the boundary. The angle between incident ray and normal line is angle of incidence. What happened to the light ray? If no change in density of medium, the light ray will travel in a straight line. So this is the line that will be passed through by the light if no change in density, this broken line. But now there is change in density. So this is denser medium. So you can see the light ray bends. So in this case, light ray bends towards normal. So this light ray, we call it refracted ray, and the angle between normal line and refracted ray is angle of refraction. Okay, now let's discuss further. What happened to the light ray actually when travel from less dense to denser or denser to less dense? Okay, in this case, we have air and glass block. You must understand that this concept, I think you all know that glass is denser than air, meaning the density of glass is higher than density of air. Okay, look at the first diagram here, this ray diagram. Incident ray, incident towards the glass block, meaning light ray travel from air to glass, less dense to denser. At this point, we draw normal line. So you can see here, the light ray bends towards normal. Okay, so you can see how the light ray deviates from its original path. This broken line actually is the line where there is no change in density of medium. So you can see how the light ray deviates from its original path when there is change in density. So for this one, we can explain by using this explanation. When light travel from less dense to medium, less dense medium to denser medium, what happened? Velocity of light decreases. So what happened to the light ray? Bends towards normal. So you can see the angle of refraction R is smaller than I. Okay, next situation, the second situation. Now the light ray travels from glass to air. Okay, so at point of incidence, same thing, we draw a normal line. So this is angle I, and what happened to the light ray in this case is the light ray bends away from normal. So you can see this line actually is the original line when no change in density. So you can see how the light ray deviates from the original path. Okay, so in this case, bends away from normal. Okay, so when light travel from denser medium to less dense or rarer medium, light ray bends away from normal. This is caused by velocity of light that increases, and this one will cause angle of refraction R bigger than angle of incident I. So you can see here, R is bigger than I. Okay, the different cases of refraction. So let's say this is a glass block, the blue color. If we incident a light ray along the normal line, meaning perpendicular to the boundary, this is air, this is glass, so this line actually is the boundary. So the light ray incident along the normal line, meaning I equals to 0. Okay, what happened to the light ray? It will travel in a straight line without refraction. Okay, but velocity still decrease in glass. Okay, so for denser medium like glass, light travels slower. For less dense medium like air or water, light travel faster. So in this case, when I equals to 0 or light ray incident along normal line or perpendicular to the boundary, we get angle of refraction equals to 0, meaning there will be no change in the direction for this case, but the velocity decrease. Okay, and then the second one, this is the ray diagram. Incident towards the glass block, this is angle I, so you draw a normal line here. So what happened to the light ray? From air to glass, speed decrease, thus bends towards normal, so the value of R becomes smaller. Now the light ray continue to travel to this point and then coming out or emerge from this point. So you can see the angle I here is R for this light ray. So what happened from the glass to air, speed increases again, so the emergent ray, you can see that come out here, will refracted away from normal. Okay, so this situation, different cases of refraction. In my previous video, part 1, we have discussed about when light travel or pass through different density of medium, the light ray will bend due to change in the velocity of light. So in this situation, we have two diagrams here. The first diagram shows light ray travel from water to perspex. So I think you know that the density of perspex is higher than water. So in the second diagram, we have water to glass. So glass is denser than water. So this one is stated by this value. What is this value? Denoted by N. Later we will discuss this one. Okay, look at the first diagram here. Angle of incidence for both diagrams are same, 50 degrees. So in the first diagram, when travel from water to perspex, the light ray bends towards normal at angle 42.8 degrees because it travels from less dense to denser. And this broken line represents the original path of light ray if no refraction occurs. And the angle between the original path and the refracted ray here is theta, also known as angle of deviation. For the second diagram, light travel from water to glass, same thing, less dense to denser. So the light ray will bend towards normal, but at smaller angle, 37.9 degrees. So you can see the angle of deviation here is marked as alpha. Okay, so angle of deviation is the angle that measured between the original path of ray without refraction and the refracted ray direction. Okay, so as you can see from here, the value of alpha is greater than theta. So if the angle of deviation is greater, meaning the medium bends the light more. So we can discuss this one in form of by comparing the density of the medium. So look at the diagram here. We have three medium: water, perspex, and glass. So if we compare the density, we have density of glass is greater than density of perspex, greater than density of water. As we discussed earlier, speed of light decreases when density of medium increases. So or we can say that light bends more in denser medium. That's the reason why you can see in glass the angle R is smaller than in perspex. Okay, so meaning in glass light ray bends more compared to perspex. So the ability of the medium to bend the light is known as refractive index, or we denote as symbol small n. Okay, so now next we want to discuss what is the meaning of refractive index. Okay, let's say we have two situations here. Light ray travel from air to perspex. Second, light ray travel from air to glass. For the density of air is the lowest one, which is equals to density of light ray in vacuum, 3 times 10 to the power of 8 meter per second. So this one we put refractive index of air is NO. And then for perspex we mark as N1 and the angle of refraction as theta 1. In the second diagram, for air we put as NO. For the second medium, glass, the angle of refraction is theta 2. Now we want to use Snell's law. According to Snell's law, the ratio of sine I over sine R is equals to constant. Then we can get, if you want to determine refractive index of this medium, perspex, what you do, you just put N1 equals to sine theta, which is angle in air, sine theta, divide by sine theta 1. Okay, and then for N2 is equals to sine theta, which is angle in air, divide by sine theta 2. So we have two equations here, 1 and 2. Now I want to relate between N1 and N2. So what I do is take equation 2 divide by equation 1. So I get N2 over N1 equals to sine theta 1 divide by sine theta 2. Okay, or we can just rearrange. So we get N1 sine theta 1 equals to N2 sine theta 2. Actually, this expression also represents Snell's law. So this one I show you how we get this equation for those who cannot get how to derive the equation. Okay, so we are going to use this equation to solve calculation problem later. Okay, now how can that formula coming or produce a Snell's law? So if you look at this diagram again, let's say the medium 1 is medium air here. So when medium air n equals to 1. So if we use the same formula again, when n1 equals to 1, here we substitute 1. Thus we get n2 equals to sine theta 1 divided by sine theta 2. Okay, or we get from here sine theta 1 is angle in air, divided by sine theta 2, which is angle in medium. So that's why we get the same formula, n equals sine I divided by sine R. Okay, so you can use both of the formula, depends on the question given. Okay, now we want to discuss further about refractive index. Just now we have discussed that the refractive index is the bending ability of the medium. The denser the medium, the more the light ray will be bent. Okay, so refractive index N determines the degree to which light bends when traveling from vacuum to a medium or air to the medium. So also we can write down refractive index is the ratio of speed of light in vacuum to speed of light in medium. So we have another formula. So n equals to speed of light in vacuum divided by speed of light in medium. So n equals to c divided by p, where c is speed of light in vacuum, 3 times 10 to the power 8 meter per second. Now introduce to you two formula for you to calculate refractive index n. How we relate density to refractive index? As we know that denser medium will bend the light more, meaning the ability to bend the light is more. Or we can say refractive index is larger. So you look at here the table, vacuum and air, refractive index N is equals to 1. So you can see olive oil, refractive index is 1.46, perspex 1.50, glass 1.52, glass flint 1.66, diamond, the denser one, 2.42. Okay, so meaning from here we can see how the speed will change when travel pass through the medium stated here. So we can relate between density and refractive index. The higher the density of medium, the higher the refractive index of the medium. The higher the refractive index the medium, the lower the velocity of light in the medium, meaning the higher the refractive index of the medium, the larger the angle of deviation, or the light bends more in denser medium. You don't need to memorize all the value. If there is a calculation problem, all the values will be given. Okay, now let's look at another situation. Okay, on refraction. So fish appears nearer the water surface. You can see the person observe a fish near to the surface. Okay, but actually what he saw is not the real fish. That one we call it the image. Because of our line of vision is straight line, so we cannot observe, which is bends, the light that bends here. So we observe along the line of vision, that one is the image of the fish. So the depth of the image is apparent depth. So I think this one is marked wrongly. Yeah? So it should be small h here, and this one is capital H. So this is the image. So image is apparent depth. For the actual depth, this one is the capital H. So we have this formula. Refractive index N can be calculated by using the value is real depth divided by apparent depth. Okay, so you must make sure you don't get confused with this one, because this one is labeled wrongly. Yeah? So this one is small h, this one is capital H. So we have the formula for refractive index, real depth divided by apparent depth. Now look at the problem solving, because we have discussed a few formula. Okay, let's look at example 1. Figure 6.14 shows light ray traveling from air into a plastic block at angle 60. Okay, refractive index of plastic is 1.49. Calculate A, angle of refraction. So now from air to plastic, so we can use the formula from the Snell's law, N equals to sine I over sine R. Here, sine R equals to sine I over N. So here I is angle in air, so we take as 60. N is 1.49. So you just use the calculator to calculate the value of angle. So we have R equals to 35.54 degrees. Second, you want to find speed of light in plastic. So use formula N equals to C over V. As we know that C is speed of light in vacuum or air, which is 3 times 10 power 8. Then you substitute, you get speed in the plastic is 2.01 times 10 power 8 meters second negative 1. So it should be lower than 3 times 10 to the power 8. Because the value of 3 times 10 to the power 8 is the highest value of speed. Okay. Example 2. When coin inside a beaker containing solution is observed, image of coin is seen at the height equals to 2 over 7 of the depth of solution. What is refractive index of the solution? Okay, so we want to find refractive index. So we must find what is real depth, what is apparent depth. So given a small h, Sorry, given is the height of the image from the bottom part of the beaker is 2/7h. But we don't want to use this one. We are going to use is the real depth and apparent depth. So the total height here is h, capital H. So this one will be the real depth. The apparent depth is measured from the surface of water to the image. So small h, we have actual depth minus height 2/7h. So we get apparent depth. Now we substitute into the formula, so the h can be cancelled, thus we get 7/5, then n equals 1.4. That one is refractive index of the solution used in figure 6.15. Okay, now let's discuss formative practice 6.1. You can try as exercise first, then you can check the answer. Okay, number 1, figure 6.16 shows the path of light which travel from medium 1 to medium 2. Okay, so the angle I equals to 75, angle R is 55 here. A, write an equation to relate light that travel through the mediums. So we have medium 1 and medium 2. That's why we use this formula. N2/N1 equals to sine theta 1 divided by sine theta 2. Okay, B part, determine refractive index for medium 2 if the speed of light in medium 1 is 3 times 10 power 8. So use N1 equals to C over V. But now we discuss about speed of light in medium 1 and medium 2. So they have same speed of light. So thus we have 3 times 10 power 8 divided by 3 times 10 power 8, thus equals to 1. Okay, because given speed of light in medium is 1. Okay, medium 1 is 3 times 10 power 8. Okay, so you want to find for medium 2. So air to glass. Okay, so for N2, N2/N1 equals to sine theta 1 divided by sine theta 2. So we substitute the value of N1. So N1 equals to 1. Thus we have N2 equals to 1.18. So you can use calculator to calculate this. So part C, what is speed of light in medium 2? Then we use N equals to C over V. So V equals to C over N. C is 3 times 10 power 8. N we have calculated here is 1.18. Thus we get V equals to 2.54 times 10 power 8 meter per second. Okay, so you can try first to answer question number 1, then only you can check the answer. Okay, question number 2, figure 6.17 shows a tank filled with oil to height 3 meter. Then oil has refractive index of 1.38. What is apparent depth of tank as seen by observer from above the tank? So same thing, we are using the same formula. N equals to real depth divided by apparent depth. So apparent depth equals to real depth divided by N. So the real depth here is 3 meter, meaning the total height of oil here. Okay, divide by 1.38. This is the refractive index of oil. Thus we get 2.54 meter. So this is the image of the depth of the tank, meaning the bottom part can be seen a bit closer to the surface. Okay, now effects of refraction also can be observed in our everyday lives. For example, why during dusk and dawn the size of the sun is bigger as compared to noon? I mean, at noon the sun is light exactly above our head. Okay, now this one can be explained by using concept of refraction of light. As you can see here, when the sun is exactly above our head, when you look up, okay, the light ray that gets into your eyes is along the normal line, meaning there will be no refraction. So what you observe, the size is smaller because the sun is very far from Earth. Okay, during dusk or dawn, this one dusk or dawn, so you can see the light ray will be refracted according to the density of the layers of air that produce here. Okay, So this one is dawn and dusk. So due to the refraction, it will cause the size of the sun observed is much bigger than the original size. Okay. And this one, like twinkling of stars, does the star actually twinkle, or it just stay at rest? This one also can be explained by concept of refraction. So light also travel from rarer to denser media, or less dense to denser. So this one will cause the light ray to bend towards normal. Okay, so at night there is also convection current. So the convection current and at the same time refraction will cause the position of the star to shift or move, right? So what you observe actually, the movement of the star is due to refraction and convection current. So it looks like it's twinkling. Actually, it stays at rest. Okay. Now this one is phenomena of refraction of light. So I think that's all for this part. So you can search more on the internet to understand.
For this experiment, you will need a power pack, a ray box, ruler, protractor, pencil, glass or perspex block. You probably need a rubber, and you need a blank bit of paper. Okay people, drawing ray diagrams to show the refraction of light through a glass or perspex block. Step 1, we are going to put the glass or perspex block down flat on our page, and we are going to draw around it. Step 2, mark a point approximately halfway along the longer side of the glass block, and then you're going to use a protractor to mark a point that is 90 degrees from there, from the edge of the block, and we're going to draw in a line that is called the normal line. Note, I have drawn the normal line on the outside of the glass block and about halfway through the glass block. You do not need to draw it all the way through. And we can label that normal line. Step 3. The glass block is now back on the page. We have switched on the power pack, and so our ray box is on, shining a ray of light through the glass block. So what you've got to have in your diagram is are lines that show where the ray of light went. And it's very difficult to fit a ruler in here and draw the lines now, so we won't do that. We will plot points that we can join up later. So you shine the ray of light so that it hits the glass block exactly where the normal line has been drawn. So you're shining the ray of light at the point where the normal line hits the glass block. We then plot a point showing where the ray of light has come from. And now the tricky bit. You might be able to just faintly see that it looks like the ray of light is moving along here. But of course it can't be, because if you look, it's clearly emerging at this point. So what we do is we mark, again we plot where the ray of light is going, and we very carefully mark a point, the point, where the ray of light comes out of the glass block. Like so. Okay, final step, all we need to do is join up the points. So the ray of light came from this point here, and we put an arrow on to show the direction the light was travelling in. The ray of light emerged from here and went through this point, so we can draw that ray of light on, and again we can put an arrow showing the direction of the ray of light, and that means that within the block the ray of light must have travelled along that path. Now you can see the light has not travelled in a straight line because it's been refracted by the glass block. What we then do is we can measure our angle of incidence, that's angle I, and our angle of refraction, angle R. The other thing you could do is mark, I won't show you how to do this, but you mark a second normal line at this point, and you can measure your angle of incidence and angle of refraction on this side as well. Alright, now it's your turn. Good luck.
tak boleh buat kerja kalau komputer.